Swayam Prabha. Digital India. Educated India.
Do you guys have tea? Can we begin? You are ready, others are not. Okay, done? Okay, so I find it hard to lecture when there is some conversation going on. Okay, so now we will sort of use ideas which we learned last lecture into actually making very nice concrete predictions on things. Okay, so we are going to model the system. And the system is really very simple. It's a box. It's a three-dimensional box, but I can only draw 2D. It has volume V, and it has a gas of n atoms. Atoms, molecules, doesn't matter. Is the system clear? Okay, so we'll assume that the box is fairly large. Okay, so one technical assumption is that we'll assume it's a dilute gas. Okay. Okay, but n will be still order of Avogadro's number. Even if it is 1,000 times less than that, it's still a big number. Okay, so n is around some big number, and we're going to make some more assumptions about the system, which you will see is that system is homogeneous. That means if you pick some any point here, they are not too different from each other. Okay, doesn't matter which. I mean, you might say, if I come close to the wall, etc. But the system is so big that we will ignore such effects, boundary effects. Okay, so all points . So that's what homogeneous means. Wherever you go. Okay, so if I want to measure density here, in general we would expect it to be the same. Okay. Second assumption is something called isotropy, which means no preferred direction. Every direction you look looks the same. I mean, for instance, living on Earth, isotropy is violated in many ways. There's gravity acting, it's picking you a preferred direction downward. Okay, but in this gas, we'll make this. This is the assumptions of this gas. Okay, so we will study two properties of this gas. The first property we want to ask is the following, which is that, let me go back there. So I'll pick a small volume, little v, okay, and we'll assume v is much less than capital V. Okay, but I said that there are 10 power 23 things. Suppose v by v is, even if it is like something like 10 power 10 smaller, it will still have some 10 power 39. So it will be a large number of. So little v might contain, doesn't have to be so small. Okay, so this condition is not very restrictive. Okay, and so what we want to ask is, and this is a system is not static, right? It's not like all the atoms in the gas, they are moving around, they are colliding, all sorts of things with the walls, among themselves. So it's keep on arranging. So if you stay in one spot and then at every instant in time, suppose we sat and asked how many particles are there. Okay, so experiment 1 is pick a spot, okay, and count the number of particles in V as a function of time. Okay, so we can do m measurements. So I will get something there is some sound somewhere. Okay. So, do we expect n1 equal to n2 equal to nn? Oh, okay. Forgiven. Do we expect them to be the same? Because it's a dynamic thing, right? Some particles will come in, some will go on, it will keep changing with time. This is experiment 1 we can do. E2, pick m locations. So think of a cube, identical cubes. They don't have to be even identical, but let's make it simplified. Identical with all of them have the same volume. Okay, again, and pick in one instant of time, I will measure the numbers in each of them. Again, do we expect them to be the same? We don't, right? So, but these two are different experiments. One is...
Sir, but isn't it just like tossing one coin?
Exactly, that's the point. I'm getting to that. Yeah, you're just a little bit, couple of minutes ahead of me, okay? So, but the point here is, so this is like an ensemble picture because we are taking M. So, we'll call this the ensemble. And this will be the time picture. And as somebody pointed out, this is like our coin toss experiment. What I'm doing is I'm doing that experiment, but I'm doing it in a particular way. Okay? So is this clear, the setup? So average number of particles this is what we would define. Okay? Right? And so one thing we will see is that if we take M to be large, it will start going towards, okay? So, and we can also do a density, average density. That would be, which we wrote here. Right? Now, question to you is, what is the average number density? What is it we would expect? Like in coin toss, we said we expect half of them to be. What would be the analog here? What should this go to? Yeah, somebody said something? Okay, so this is our expectation, and how do we go about showing this? Okay, so the idea here is to map this problem okay. So I will define, so it's a, I need to have a sample space. So sample space is closer to what Siddharth was saying, cat is alive, cat is dead, particle is in the box inside the volume, or okay, so sample space for one particle is either in the box or outside the box. Okay. So if we focus on one particle, we label it, and okay, and let's call this probability P, little p, and we'll call this 1 minus p. Now we can do better than this. What do you think I should choose for p? Okay. No, and nothing. One particle only. There only one particle. Okay, this is very natural. What this says is your system is homogeneous, so it doesn't matter where you are. Okay, so this value should be, it should tend to something, at least on an average. This is what we should expect. That. So this is what we should expect. Now you can see this situation, little v upon big V is very, very small number, which is quite different from our coin tossing experiment. So now, okay, so this, so is this map clear? Yes. So it's now we are done. Okay, we want to ask what is the average we want to ask what is the probability of finding m particles or atoms and I'll call it P of m. What should the answer be? Binomial distribution, right? So what we have now is something so cute. We don't know much about the system except we made the homogeneity assumption. I've not used the isotropy out here, but homogeneity tells you it has to be something like this, and it comes with a value of P. Tells you what P is also. Is this answer clear?
Yes.
Okay.
In certain cases, in this example, in certain cases we actually took the homogeneity into account and
Not certain places. It's over. I mean, I've done it. I've said every point. So that is also something which would require homogeneity tells you that E1 and E2. Actually, ergodicity also is needed, but even what it says really is that these values will not be any different.
if it was really homogeneous, you would also say
No. It's not in that sense. It's homogeneous on an average. I mean, that means no point is special. And it's not saying, we are not making the assumption that it's a static thing where everything is nailed to those points. It's a very dynamical thing. So it doesn't make sense. N is allowed to fluctuate. The number of particles inside your test volume is allowed to fluctuate. Why not? And we are telling you what the probability is. We are giving you a concrete answer.
So we are just taking the points to be uniform, but not the number.
Yeah. So no, it says no, there's no preferred location. Every point is the same as the other point. And okay, and ergodicity means even if you let it, if you measure, if you make the measurement now, or if you make the measurement tomorrow or in the afternoon, it won't change. That's the idea. So this is also the idea of equilibrium. Your system is in equilibrium, measurements won't change. Okay, so this is what we have. So now we can go ahead and ask, what is the average number of particles in the gas? So I will just write out answers. So the mean number of particles, mean or average number, is given by n times p for the binomial, but we have a concrete value for p. Okay, and let me just call number density, I'll use the symbol rho. But we can talk about fluctuations now. So that is a variance, which is sigma square, this. So p is pretty small, so p square I can throw out. Approximately it is n into p. So it says, what does it say about sigma? It says sigma goes like root n. Let me also write it in this. This is also np. Yeah, if I neglect this, it's np, it's still rho v. Okay, but we know what the corrections are. But I just want to keep the n here to tell you one point. It says sigma goes as root n. Okay, and mean value goes as n. Don't worry about factors. So we can compare. So mu is this thing, and it says these fluctuations. So mu by sigma goes like 1 by root n, which is again sort of, so this is the relative fluctuations. Okay, so this goes like 1 by root n. This is a very, very important result. It says that as you go to n to infinity, the fluctuations become smaller. Yeah. Oh, sorry, root n upstairs. Thank you. Okay, so it says something like n plus or minus root n. This is how you would quote your result. And if you pull out this n, this falls like 1 by root n. Correctly, you would write mu plus or minus sigma, but I'm only tracking powers of n. Okay, so this agrees with our intuition that the more measurements you make, you will start, the fluctuations will get suppressed. Okay. So in physics, what we would like to do is to we would like to take the volume of the system to infinity, but we'll also want to take the number to infinity such that the ratio, the number density is kept constant. Okay, this is called the thermodynamic limit. Even though our systems in our labs are small, we would like to think of them as infinite systems. Okay, so we'll call this the thermodynamic limit. n tends to infinity, v tends to infinity, but n over v is kept to be rho. Because if you change the density, we are changing the problem altogether. So if you want to double the system, you double the volume, double the number, so that the density will not change. So what we want to do is to take the thermodynamic limit of this formula. Okay, so the idea here would be to get rid of all powers of n in some sense, because n is going to infinity, and write n upon v, etc., and try to write it in this fashion in terms of quantities which are not blowing up. So we want to do of P of m. I will now expand things out and replace things so that by m factorial, and P was V okay, and m is going to be kept, m is some finite number, n is going to infinity. So what we can do is replace all these n's with n power, little m is much smaller than this. Okay, so this is, I can approximate this whole thing by n power m, and I can take it into this. Okay, so okay, so this, I've taken care of this, but this remains. But again, out here m is very small, so I'll approximate this by n itself. Okay, so now we can see there is some simplification that happens. Where is the duster? I left it somewhere. Under what? Here. Yeah, that's the obvious place to look. Are you with me so far in my steps? I've just said used m is much less than. Okay, nothing fancy. But now this n by v I can replace by rho. So this is equal to 1 by factorial m factorial rho little v power m yeah. Because m is much n, I'm taking capital N to infinity, m is some finite number. So n minus m plus 1 is the same as n. Each one I'm calling n minus 1 is n. In that limit it makes sense. Okay? Does anybody know what is this limit? Huh? It's not 1. It's so it's very weird. Yeah, this is becoming small, but this is also growing. So this is another beautiful formula which says that limit same exponential function. Okay, believe me. But you don't have to believe me. This has to be correct. because total probability has to be 1. So now what I get, what is this? Have you seen this? No. It's the fish. Poisson. It's the Poisson distribution. But we already saw some hint of it, which was that the variance also went as NP. It turns out for Poisson distribution, both the mean and the variance have the same. Okay.
Initially, it was in the form of a binomial.
Yeah, but after the thermodynamic limit, it becomes Poisson. So Poisson is a better model than, in some sense, than
So can we say it goes from being a binomial distribution to a Poisson distribution?
that's the correct statement. In that limit, in the thermodynamic limit, which is well defined. Okay. So I mean, for practical purposes, Avogadro's number is good enough to be infinity. So in that sense, Poisson is good. Okay. So is this clear? So our simple coin tossing experiment, which we sort of made a little bit more general by letting a P be this thing. And so we have actually seen 2 of our distributions show up in a very natural physics fashion. Okay? So this tells you something about the density of the gas. Now I will again try to address a different question, and the question is, I want to ask how are the velocities of the particles, distribution of velocities. That's our second example. Okay, so you pick a particle, it has a velocity, it's a vector. So it will have an x component, y component, and a z component. I guess you know what this is, right? Okay, so what is the speed? Okay, so, but now let's look at Vx, Vy, Vz. What is the range of values they can take? Any value, right? Of course, you might say speed of light. Okay, we are working in systems where speed of light is effectively infinity. I'll make that assumption. It's not so important, that assumption, but okay. So we will say Vx, Vy, Vz take values in R. Okay, and we will think of them as some kind of random variables. Okay, so first thing is that so we would like to ask, I can ask the following question: what is the let's say that P of Vx delta Vx. Now because the continuous variable, I have to use is the probability. This is a density, so I have to multiply it by delta Vx to get a probability. Is the probability of the particle having velocity x component of velocity in the range in some window with width delta Vx. Okay, so this is the density. Okay, but now comes the interesting thing. I've said my sample is isotropic. Doesn't matter if I pick x, look along the x direction or the y direction or the z direction. It should be the same function. I don't know what it is, but it has to be the same function. Okay, so same distribution, same function, Vy and Vz. This is isotropy. Actually, we could have been, if in higher classes, I will talk about this, depending not only just on the velocity, it could depend on where I am in the gas, but we have said homogeneity, so it won't depend on position. So it will only depend on these guys. So now we can say that if you give me, so we are in 3 dimensions, so the velocity is some vector. So I can think of a cubical box with sides delta Vx, delta Vy and delta Vz. This is in V space, but that's also 3-dimensional space. So I can now, and we'll also make this assumption that Vx, Vy, Vz are independent of each other, which is kind of true from physics viewpoint also. So now, this is the probability of finding the particle in a cubical this thing with, so the picture is like this. I picked some spot and I took some volume with sides. I'm not writing what the sides are. You can see it from here. A cuboid with sides. I don't know this. I don't know any of these P's, but this is just telling you this. But now comes the thing, the following point, that this guy is still picking out x, y and z directions. I can change my axis. Someone else can choose something else. X prime, y prime, z prime. Okay, they'll be orthogonal to each other, all that is fine. So this still has some weak dependence on isotropy, but the only function of this which doesn't depend on this direction is what? Its magnitude. Okay, but magnitude is little bad, speed is bad because it involves a square root, which in mathematical terms is a square, it's not analytic. So we will take the square, okay. So, but this, so it's further, isotropy implies that this guy should be a function not of Vx, not of Vy, not of Vz, but only on the combination, okay, this some other big function P, I don't know what that is. It depends only on the square of the speed. So this problem is now reduced to a simpler problem. It says find the function, if at all, find a function which has the property P such that if I take the product of them, it should come in this form. How much time do I have? Because we started late, so. Huh? Oh, that's a lot of time. Okay. So, yeah, I will need only 10-15 minutes. Yeah.
So what do you mean by saying that the square root is not analytical?
Don't worry. It's some mathematical nonsense.
What is it?
Square root is not unique, plus or minus. That's why. That's its ambiguity, and there is a sense in which you can go, if you think of them as complex numbers, you can go smoothly from plus to minus.
So if we take it and convert it to higher power of square or something.
Square, yeah, it is fine. Square is fine, cube root is not. I'm taking in the minimal thing, which is this. Okay? So this is what I want. I want to find a function P which has this property. Is the problem clear? It will turn out that this function is almost unique except for one free parameter, that's all. It's an argument claim. It's a very simple argument. First step we did was to say that Vx, Vy, Vz are independent. That's also I use isotropy, but in a very weak sense, and said these better be the same numbers. That's all. No, we will prove it. You will see. And that parameter has a physics meaning. There are 10 more minutes. It's like, the punchline of the story. I'm giving it to you because some people may get bored, but they can remember this. Especially people who, sometimes I remember as a student, some teacher will emphasize something and you do not understand why they're emphasizing them. Why is that crazy person saying the same thing? And then 5 years later, something like it can be of the order of the years. Oh my God, that's why this person was saying that. You only remember the irritation with that person, but you don't. Then you recall. That's also a nice way to recall something. So anyway, so if people forget what I said, they will at least remember this fact, whatever I told you. But now we will derive that. Okay. Now this requires a little bit of calculus. Apologies to you guys, but I will do it and I'll give you some intuitive feel for that. Okay. So. Hopefully you guys know how to what a derivative is, right? That's all I want. I don't need some fancy stuff. Okay. So the idea is that we will keep Vy, Vz constant. Okay, we won't worry about what they are. They are some numbers, fixed numbers. Yeah. So I don't have to get into partial story. I don't want to get into partial story. Okay. So now so what I have is this P of Vx, P of Vy, P of Vz is equal to okay. So what I will do now is take a derivative of this with respect to V of x. In other words, I will change V of x. Okay. So if I take derivative of that, this is the only term which will contribute. These are not independent of that. So I get dp by dvz vx of p of. But now this is some constant, but it's viewed as a function of one variable. It's a function of v square, vx square. So I will just write this as dp by dvx square, but now I need something called chain rule, which says that you do derivative with respect to d of vx square by dvx. But this is just 2vx. Okay, is this clear?
Yes.
Okay, so now just to simplify things, I divide everything by this quantity. On the left hand side, this is equal to this, I divide by p. Advantage of that is that these terms disappear. So I get 1 by p of vx okay. So what I will do first is now I'll divide both sides by v of x for a simple reason. Leave this 2 can also be okay. Okay, it's the same equation. I divided by 2v of x. Okay, so left hand side, this is a function of vx. There is no dependence on vy and vz. Do you agree with me? Yes. Absolutely. This is only a function of vx. What about the right hand side? It's a function. It might be we are doing derivatives with vx square, but it's really a function of all of them. So what this is saying is that the left hand side is a function of Vx alone, but right hand side is a function of both all Vx, Vy, Vz. How can that happen? Is there any way out of this? Hmm? No. See, this is a function of only of Vx, independent of Vy and Vz. How can a function, do you know any function of one variable which can be equal to a function of three variables? Not equivalent, nothing. They are not equivalent. They are not equal. They are different numbers. I can change Vy and Vz. For this purpose, I kept it constant. This can happen only if both of them are equal to a constant. This is, sorry, I forgot to put 1 by p. Okay, and let's call this constant minus alpha. It did, no, they didn't. I only took derivative over respect to v square, but here I used a chain rule. Actually, it should be d of, but these are constants from our viewpoint. I didn't want to get into partial differentiation. So this thing has, this right hand side is a function of the combination Vx square plus its combination of, it's speed square. It's a function of that. So this constant, I'll call it minus alpha. Okay, so now we can ask, okay, so this, we already saw the differential equation which I defined the exponential. You can check that this implies it's equal to exponential of Vx square, because if you look carefully, that's what it is. And capital P is very easy to check that this proportionality constant has to be the same. Okay, and now that property we wanted has come, and I have delivered what I said. I said the function is unique up to one undetermined constant, which I am calling alpha. And this proportionality factor I can fix by saying that it has to be normalized. Integration of that should be this, so we can fix that. Okay, so is this clear? What the function we have given satisfy the required property, and it is unique up to this factor. Now the physics question is, what is alpha? Okay. So m is the mass of the particle, kb is something called Boltzmann constant, so it is determined by the temperature. Okay, so here's what it says. This, if you look carefully now, if you look at this, it's the Gaussian distribution with mean 0 and alpha zero equal to mu. That is, the mean velocity being 0 is obvious. The probability of it having plus v and minus is the same. Isotropy tells you that. Okay, so mu is 0, so it's the Gaussian. So the other example shows up here, and so if you put all the, I've given you mu and sigma. So you see that the sigma, so sigma square is proportional to kb times t. It says that as the temperature increases, the velocity spread increases. Average velocity doesn't, but the spread, it becomes wider. Okay, so this free parameter has a physics interpretation. This is where your model tells you what it is. It says, and this has a name, it's called the Maxwell-Boltzmann distribution of velocities. It must have come in chemistry, because chemistry they are like only 5 years ahead of physics. It hasn't come yet? Physical chemistry is what, 12th standard, is it? It will come in chemistry somewhere. Okay. But it's what is kind of cute here is that just pure thought and putting in certain conditions, we are able to actually bring it down up to one parameter, and then physics tells us what that parameter is. M is the mass, by the way, of the particle. Okay.
So what is the parameter called?
Called temperature. I have a physicist. For me, this is M and K. This is a known constant. You give me the gas, I know the mass. So for me, it is temperature. It's some complicated. Alpha is not. It's some number, known number. If you give me the gas, I give you the number. So it's alpha is like temperature. That's all. So the parameter for me, I'm a physicist, is temperature. Okay. So it's kind of very nice that we are able to, with some simple assumptions, and hopefully I have sort of removed the barrier between maths and physics. There isn't one. Okay. Don't go about saying, oh yeah, that thing is some mathematical nonsense. No, it maps to, it lets you model lots of things. Okay. And by the way, if you want to trouble somebody about quantum information, quantum computing, he's coming in the afternoon. Arul. Okay, trouble him. Okay, so he's the expert. Okay, so I'll pause for questions or comments.
I will just ask for a quick clarification.
Yes.
So PBX, PBY, PBZ, B square related to P is
P of one, it's a function of only one variable called B square.
Yes, sir, yeah.
That's all.
And we said P is equal to PBX, PBY.
It should be. That's all.
Yeah, understood.
That's all. I'm sure there are. I mean, by what we are doing is by consistency fixing it. Okay. Actually, the question is, what happens if isotropy is broken? If there's a particular direction and things like that. Okay. So those kind of things we can handle. And that will tell you, so for instance, I could give you some drift in some direction. And so what that will do is, let's say it's in the x direction now isotropy is broken, but there is still isotropy in the sense of y and z, there is still that thing. So it will still look like this. So you will get something similar to this almost, but you will find that the drift will be accounted for by saying that mu of Vx is not 0. So you can accommodate that into, so small deviations from that, we can actually put it into that. So only thing I want to tell you people is please learn to enjoy the process of learning. Learning is fun, and I just want to tell you that one is a student I'm finishing 30 years of teaching here. So, and so I'm still learning. I'm still a student first and professor second. Okay. Of course, because of, as time goes on, you learn more, and I learn a lot teaching you people, etc. So it's also about how to present things. It's easy to do something in your own page. It's very difficult to come and stand in front of people and talk in a fashion. So you should practice that. Talk to your friends. And then your friends are the toughest critics, you'll find. That if you can convince your friend, not your teacher. Teacher knows the stuff. So you have to convince your friend. You actually understand things better. So that's some process which you should interact with each other. You people are the phone generation. I know that, one-handed generation. One hand always has a phone. So get out of that and talk to each other. Trouble each other. Okay. All the best.
Swayam Prabha. Digital India. Educated India.